Welcome to the fourth lesson in Session 4, Rationalizing the Denominator. Remember from Lesson 4.2, we discussed the characteristics of simplified radical form. The three characteristics of simplified radical form include: number 1, the radicand can have no perfect square factors. Number 2, the radicand cannot contain a fraction. And number 3, the denominator of a fraction cannot contain a radical. The multiplication and division properties of radicals that we learned in Lesson 4.2 help us with the first two rules. In this lesson, we're going to learn how to properly eliminate radicals from the denominator. When writing mathematical expressions, it is improper to leave a radical in the denominator. Rationalizing the denominator is a process by which a fraction is simplified so that the denominator contains only rational numbers. This lesson will cover three cases. 1, rationalizing a monomial denominator, where the denominator and the radical is a single term, in this case the square root of 3. Number 2, rationalizing a binomial denominator, where the denominator is two terms, in this case 2 and the square root of 3 create the binomial. And number 3, rationalizing a complex denominator, where the denominator is a complex number, in this case 2 plus 3i. So a monomial denominator, a binomial denominator, and a complex denominator. To rationalize a monomial denominator, we manipulate the fraction to create a perfect square in the denominator. To do this, we have to analyze the radicand and identify the smallest perfect square multiple. Second, we have to multiply the numerator and the denominator by the same number to create the perfect square in the denominator. Here we'll have three examples. In the first example, we have 1 over the square root of 3. So we have to rationalize the denominator. So in order to do that, the smallest perfect square multiple of 3 is 9. So in order to produce that 9, we have to multiply the numerator and the denominator by the square root of 3. Multiplying fractions straight across gives us the square root of 3 over the square root of 9. Now we simplify the denominator, the perfect square down there, the square root of 9 gives us 3. We end up with the square root of 3 over 3. Now those 3's cannot cancel out. The 3 is expressed as a radicand in the numerator and the 3 in the denominator is not. So those do not simplify. Root 3 over 3 is our answer. Now in the next example, we have 3 over the square root of 6. The smallest perfect square multiple of 6 is 36. So in order to produce 36, we have to multiply the numerator and the denominator by the square root of 6. And multiplying fractions straight across, we get 3 root 6 over the square root of 36. And simplifying that denominator gives us 3 root 6 over 6. Now, while we cannot cancel out the 6's because the 6 in the numerator is expressed as a radicand, we can simplify this fraction because the 3 and the 6 both contain a common factor of 3. Dividing out the 3 gives us root 6 over 2. Now our last example is 1 over the square root of 8. The smallest perfect square multiple of 8 is 16. So in order to turn 8 into 16, we multiply by the square root of 2 over the square root of 2. Multiplying fractions straight across gives us the square root of 2 over 16. And simplifying the denominator, simplifying the square root of 16 gives us root 2 over 4. And again, since the 2 in the numerator is expressed as a radicand, it will not be able to cancel out with the denominator. So root 2 over 4 is our answer. Next, we're going to rationalize a binomial denominator. To rationalize a binomial denominator, we have to multiply it by its conjugate. The conjugate is formed by negating the second term of a binomial. So here we'll have a list of binomials and we're going to produce their conjugates. First, we have 1 plus root 3. Its conjugate is 1 minus root 3. Notice we're just negating the second term of the binomial. Next, 2 minus the square root of 2. Its conjugate is 2 plus the square root of 2. And lastly, we have root 5 plus root 3. Its conjugate is root 5 minus root 3. Now the purpose of its conjugate, what's the benefits of it, is when you multiply a binomial by its conjugates, the radicals will get eliminated. We'll show you an example with 1 plus root 3. Its conjugate is 1 minus root 3. and we'll see what happens when we multiply these two binomials. So we're going to use the FOIL method, so we multiply the first two terms. 1 times 1 gives us 1. The outside terms, 1 times negative root 3 is negative root 3. Move to the inside terms, root 3 times 1 gives us positive root 3. And the last terms is root 3 times negative root 3, which gives us negative root 9. When we simplify that, we'll see that the two middle terms, negative root 3 and a positive root 3, add to 0. Those are opposites, so they're going to add to 0. And we simplify the square root of 9 as 3. So when we simplify the binomials, or simplify the expression, we end up with 1 minus 3, which is negative 2. So you see, if we multiply a binomial by its conjugate, we end up with a new term with no radicals. Here are a couple of examples on rationalizing binomial denominators. In our first example, we have 3 over 5 minus root 2. So the denominator is where our focus is 5 minus root 2. We recognize it's a binomial denominator with a radical, so we need to identify the conjugate and multiply the numerator and the denominator by the conjugate to find a new equivalent expression that has no radicals in the denominator. So the conjugate for 5 minus root 2 is 5 plus root 2. Multiplying the numerator, 3 times 5 is 15, and 3 times the square root of 2 is 3 root 2. In the denominator, we FOIL it out, and 5 times 5 is 25. 5 times root 2 is 5 root 2. Negative root 2 times 5 is negative 5 root 2. And negative root 2 times root 2 is negative root 4. Now the numerator in this case can't be simplified. 15 plus 3 root 2, those are not like terms, so we're done with our work for the time being in the numerator. We have work to do in the denominator. If we see 5 root 2 and negative 5 root 2, we're going to cancel out. And we have minus the square root of 4, and the square root of 4 is going to simplify to 2. We further simplify the denominator to get 15 plus 3 root 2 over 23. Now we have to look to see if we can simplify the fraction. However, in this case, our focus is on 15, 3, and 23. Now there is no common factor between those three numbers, therefore we conclude we cannot simplify this fraction. And our answer is 15 plus 3 root 2 over 23. Our next example, we have 1 plus root 7 over 3 minus root 7. So remember, we're looking for the conjugate of the denominator, and the conjugate of the denominator is 3 plus root 7. So we multiply numerator and denominator by the conjugate 3 plus root 7. Now we have to distribute the numerator, which gives us 3 plus the square root of 7 plus 3 root 7 plus the square root of 49. And in the denominator, we have 9 plus root 7 minus root 7 minus the square root of 49. So we have to simplify the numerator and the denominator in this case. Simplifying the numerator, we have like terms in root 7 plus 3 root 7, which is 4 root 7. And the square root of 49 is equal to 7. In the denominator, we have the root 7 and negative root 7, which cancel each other out, and the square root of 49 is 7. We can further simplify in the numerator, 3 plus 7 is 10, and 9 minus 7 is 2. So our simplified version here is 10 plus 4 root 7 over 2. Now again, we're looking at three values, 10, 4, and 2. If all three of these values share a common factor, then we can further simplify the fraction. So 10, 4, and 2 are all even numbers, therefore they're divisible by 2, so we can simplify divide out a 2 in this expression. So our new expression is 5 plus 2 root 7, and that's what we're going to accept as our answer. Lastly, we're going to rationalize complex denominators. When working with complex numbers, the same rules apply. Just as with radicals, we cannot leave an imaginary number in the denominator. So here we're going to show you an example of how to multiply complex conjugates. So 3 plus 2i and 3 minus 2i are complex conjugates. For the same rules, the second terms are negated. The first terms are the same, the second terms are opposites of each other. So 3 plus 2i and 3 minus 2i are complex conjugates. Now when we distribute, we end up with 3 minus 6i plus 6i minus 4i to the second. And when we simplify, we see what we want to, a negative 6i and the positive 6i are going to add to 0. They're going to cancel each other out. And furthermore, we have negative 4i squared. And remember from a previous lesson, I to the second power is equal to negative 1. So if we substitute negative 1 in place of I to the second, what we end up with is negative 9 minus 4 times negative 1. Negative 4 times negative 1 is positive 4, and 9 plus 4 is 13. So multiplying complex conjugates eliminates imaginary numbers. In our example of rationalizing a complex denominator, we have the expression 2 over 1 plus 3i. So we recognize that we have a complex number in the denominator. We need to multiply by its complex conjugate. 1 minus 3i is the complex conjugate in this case. So we multiply numerator and denominator by 1 minus 3i. Distributing the numerator gives us 2 minus 6i, and distributing the denominator gives us 1 minus 3i plus 3i minus 9i to the second. So as we simplify, negative 3i plus 3i in the denominator are going to cancel out, and we substitute negative 1 in place for I to the second. The numerator can't be simplified any further, so we just have 2 minus 6i. The denominator we simplify further. Negative 9 times negative 1 is positive 9, and 1 plus 9 gives us 10. So we get 2 minus 6i plus 10. But again, we have 2, 6, and 10. We identify a common factor between the three terms, and we have to divide that out by 2. So dividing that out by 2 gives us 1 minus 3i over 5. And lastly, complex terms have to be separated. So we express it as 1 over 5 minus 3 over 5i. And that concludes this lesson. In order to successfully get credit for completing this lesson, you must do well on the quiz. Feel free to email us if you have any questions. Good luck.